All right, welcome back everyone to Organic Chemistry 2, 2312. We're going to get started with lecture number 29. And so in the past lecture, we saw a number of ways to do aldol reactions selectively by doing crossed aldol reactions. We use thermodynamic bases such as sodium hydroxide, or using things like lithium aluminum hydride to kinetically deprotonate to make enolates with quite a bit more control. And along the way, many of the products we saw were alpha-beta unsaturated carbonyl compounds. So in this case, we have drawn here an alpha-beta unsaturated ketone. And we need to talk about the reactivity of these compounds as well. Because due to the resonance structures you can draw, you can either take an arrow and move the electrons up, and we'll make a resonance structure that explains the reactivity we've seen many times for carbonyl compounds, where we have a positive charge located on the carbon. You can actually draw alternative resonance structures on these carbonyl compounds, where instead of putting the positive charge on the carbonyl carbon, you can actually move it one carbon over further. And this can put the positive charge at the 4 position. So a lot of times we will be numbering these as 1, 2, 3, 4. So we could say the 2 carbon would be a 1-2 reaction, would be the nucleophilic additions we've seen before. And turns out sometimes we can actually have 1-4 addition reactions that take place on this more remote carbon that still has this positive charged resonance structure. So we can actually divide these 2 reagents into what we call either hard or soft reagents. So you're going to have hard nucleophiles and soft nucleophiles. So these are kind of strange. It's almost like you're giving a flavor to a nucleophile, and that's pretty much what it is. But we can notice some differences between the nucleophiles in these 2 centers. On the hard nucleophile end, these are all very reactive species. So we have our organometals like Grignards, organolithiums, or lithium aluminum hydride. Remember that all of these are able to add into things like nitriles or esters. Lithium aluminum hydride can even react with carboxylic acids. So these are going to have lots of localized charge, and specifically negative charge since they're nucleophiles. So we usually think about things like Grignards and organolithiums almost being like carb anions. So hard nucleophiles means that we have a lot of concentrated negative charge that's very reactive kind of in one place. Soft nucleophiles, on the other hand, are going to be anions or even neutral compounds that are going to be much less reactive. They're still going to be nucleophilic, but their electron density will frequently be spread out a little bit more. So if you think about a nitrile, this is an sp hybridized carbon, so it's going to be quite electronegative. That means it's going to be less reactive of a nucleophile, and it also has this electron withdrawing nitrogen on it as well. Amines are neutral nucleophiles, and we see them do alkylation reactions with alkyl halides. Frequently you can do condensation reactions with amines without having to actually deprotonate this hydrogen on the nitrogen that is not very acidic at all. Cuprates are really not very nucleophilic at all with in a 1-2 sense, but these can add 1-4. So all of the reactions where we saw all of these organocuprates not reacting with carbonyl compounds, now we have a class of carbonyl compounds where they can react. They're just going to do it specifically with alpha-beta unsaturated carbonyls, and we'll discuss that reactivity a bit more. Thiols, if you go to something like sulfur, if you think about how big a sulfur atom is versus an oxygen, it is larger. Since it's larger and more polarizable, when you deprotonate a thiol or even a thiolate to make a negative charge, it's going to have much more delocalization where you have this negative charge over a larger surface area. So this makes the anion a bit more squishy it's lower in energy because you have less concentrated charge along the way. And so thiols in general also will be very soft nucleophiles. Enolates are probably the most relevant of this section for the types of reactions you can do. And the reason that enolates are soft is because we do have this resonance structure. So it's not all concentrated on just the carbon. We have delocalization between the carbon and oxygen. So this is enough stabilization to switch it from being a hard nucleophile like a Grignard to being a soft nucleophile. Because we do have the negative charge on an oxygen and it's shared with a carbon as well. So let's take a look at some of these types of reactions. So I mentioned the nucleophiles on the previous slide. We're just going to show a couple reactions of how these things can work. So we mentioned cyanide can be a soft nucleophile. This simply means that we're going to have an attack on now this beta carbon in the 4 position. We're going to be able to move the electrons up to the carbonyl. So now the product intermediate will actually be an enolate. These usually have some sort of proton source around, like a little bit of acid to help catalyze the proton transfer. Probably just a little bit of this around. And so now we can have a final protonation of the enolate to give our 1,4 addition product. So again, this being the 1, 2, can I draw 2s today? 2, 3, and 4. Similarly, with something like an amine, now instead of adding to the carbonyl, we can have 1,4 additions when you have an option to do one of either. And then after proton transfers, we'll end up making again the bond at the more remote carbon. In the 4 position. And just to maybe show another example, I'm going to add a 3 on here for cuprates. So let's imagine we had the exact same carbonyl compound. If we were to add in diethyl cuprate, first we'd end up still making an enolate. Note that we made this new bond in the 1,4 position. And then whenever you add water to work this up, we're going to make a new carbonyl containing compound, where once again, the ethyl is attached to carbon number 4. So this is going to be great to combine with all those aldol reactions we just learned and thinking about the types of molecules we can make. You can already start to see different disconnections. So whereas previously we saw a lot of different retrosynthetic disconnections where we're looking at different types of alcohols and breaking the neighboring bond, now we can think about potentially breaking substituents that are in the 4 position and going back to an alpha-beta unsaturated carbonyl compound. So this is an interesting reaction. This involves nucleophiles which you've seen before, but they're going to do something a little bit different. So when we have hydrogen peroxide and sodium hydroxide mixed together, we know that these are in equilibrium. Hydrogen peroxide is more acidic than water, so we're going to make this peroxide anion. Turns out, since we have this neighboring oxygen, the peroxide anion is quite a bit softer than your average hydroxide molecule, and it can do 1,4 additions to alpha-beta unsaturated carbonyl compounds. What's strange is that we end up making an epoxide. So this may not be obvious at first, but if we start to push the arrows, and considering that we know that we need to make this bond in the 4 position, let's see where it takes us and how we might be able to get an epoxide out of this at the end of the day. So we're going to have the peroxide anion do our 1,4 addition. These are also called conjugate additions, so you may see that name as well. Along the way, we make an enolate anion that has a peroxide attached to it. So if we remember, enolates are always nucleophilic at carbon, and we know that this oxygen-oxygen bond of the peroxide is going to be weak. And so this oxygen-oxygen bond likes to break. So this is going to be a case where we have a nucleophilic carbon, and the oxygen here is actually a bit electrophilic. Because it does have this leaving group on it. So hydroxide, again, usually is a poor leaving group, but this will be an intramolecular reaction. Even though three-membered rings are strained, we saw in the formation of epoxides, frequently their formation is going to be kinetically fast due to spatial proximity. It's the smallest ring you can make. And we're able to directly attack on this oxygen because it does have this hydroxide leaving group. And when we do this, we end up making a new epoxide, and we make hydroxide anion that quickly will then go back into equilibrium to make more peroxide anion. So to do these reactions, actually you only need a little bit of sodium hydroxide. This would only need to be catalytic just to keep making enough hydrogen peroxide around to transfer its oxygen. So qualitatively, like in the big picture, this is similar to MCPBA, only we're going to be going through a different mechanism, but we still have a peroxide compound that is transferring its oxygen directly to a double bond. As we mentioned before, enolates are also quite soft. So whenever you have specifically the reaction of an enolate anion to an alpha-beta unsaturated carbonyl compound, this is going to be called a Michael addition. And a lot of times, even with those other types of nucleophiles, like with an amine, sometimes you'll call that an aza-Michael, or with a sulfur, a thio-Michael reaction. So here's Arthur. Once again, he lived long ago. He must have discovered this reaction more than 100 years ago. And now we can probably expect how this mechanism will work. So we have sodium hydroxide as the base. We have two different potential molecules. Cyclohexane is actually a little bit more acidic. So hydroxide will be able to take this hydrogen from the ketone to generate an enolate anion. Again, this is going to be in minor equilibrium. Since this is going to be a soft nucleophile, and we have the option of doing 1,2 or 1,4 additions, we are going to observe the 1,4 addition to the carbonyl. Note that this is also a less sterically hindered reaction. So this will also accelerate the rate. We're not trying to make these fully substituted carbon centers anymore. After attack on the alpha-beta unsaturated ketone to do the Michael addition or conjugate addition, we get a new enolate that now will be protonated by water to give this 1,4 product. So overall, not too bad, right? And once again, we end up with some new types of bond disconnection logic for making this molecule. So if we think about this in a retrosynthetic fashion, We could imagine breaking now this 1,4 bond.